Okay, so when you hear the words organic chemistry, your brain probably jumps to, crazy looking diagrams and reactions you have to memorize. But what if I told you it's less about memorization and more like learning a brand new language? A language that literally describes everything, from life-saving drugs to the deadliest poisons. I mean, think about it. What could octopus venom, the vitamin C in rose hips, and the stuff in poppies that helps with pain, what could they possibly have in common? They seem like they're from completely different worlds, right? But deep down, their instructions, their very essence, it's all written in the exact same language, the language of organic chemistry. And here's the really good news, the part that should make you breathe a sigh of relief. According to L.G. Wade Jr., who wrote the book we're drawing from, you don't need to memorize a dictionary's worth of molecules. Nope. It's all about understanding a few key principles, a sort of chemical grammar. Once you get that, you can start solving problems and predicting how things are going to behave. So, that's our game plan for this explainer. We're going to tackle this just like a language. We'll start with the absolute basics, the alphabet, that's atoms and bonds. Then we'll get into the nuance, stuff like shape and stability. After that, we'll cover the grammar, which is all about acids and bases. And finally, we'll start building our vocabulary with something called functional groups.
All right, first up, the alphabet. You can't read the epic poems that molecules write until you learn your letters, right? We have to see how they connect to form the simplest words.
And the most basic connection, the absolute bedrock of organic chemistry, is the covalent bond. It's really just two atoms sharing a pair of electrons. You can think of it like a handshake that holds the whole molecule together. And it's how carbon, the star of our show, builds the millions of organic molecules out there.
So how do we actually write these molecular words on paper? We use something called a Lewis structure. It's like a blueprint. Let's take ammonia, NH3. First, you just count up all the available electrons. Then you stick the hydrogens on the central nitrogen atom. And finally, you sprinkle the leftover electrons around to make sure every atom feels stable and happy. This simple drawing? That's our version of spelling.
But of course, the language gets a little more complex. Atoms don't have to share just one pair of electrons. They can share two pairs, which makes a double bond, or even three pairs, which makes a triple bond. Each one, single, double, triple, has its own unique personality, its own length and strength, which adds a ton of variety to our molecular vocabulary. So we've got our letters, we've got our bonds. But just like with any language, flat letters on a page, well, they don't tell you the whole story. The real meaning, the richness, comes from nuance, from things like 3D shape and stability that give molecules their power. Lewis structures are great, but they're two-dimensional. And this brings up a huge question. Do molecules actually live in a flat 2D world? And the answer is a resounding no. They exist in 3 dimensions, and honestly, their shape is everything. The concept that gets us from that flat page into the 3D world is called hybridization. You can think of it like an atom mixing and matching its electron orbitals to create totally new shapes for bonding. Methane is the classic example. Carbon's orbitals hybridize to form this perfect little pyramid, a tetrahedron. And that 3D shape is absolutely crucial for how it behaves in the real world.
Okay, let's add another layer of nuance. Take a look at the acetate ion. If we draw its Lewis structure, it seems pretty simple. You've got a negative charge, and we just stick it on one of the oxygen atoms. It looks clean, but is that what's really going on?
I mean, is that fair? Why does one oxygen get to hold all of that negative charge while the other one gets nothing? We know electrons are always moving around, so shouldn't there be a better way to describe where that charge really is? Well, there is, and it's a super important concept called resonance. The big idea here is that sometimes one single drawing just can't capture the reality of a molecule. The true structure is actually a hybrid, kind of like an average of all the possible drawings. So let's go back to our acetate ion. In reality, that negative charge isn't stuck on one oxygen. It's actually shared. It's smeared out across both oxygen atoms at the same time. We call this delocalization. And by spreading out that charge, the whole ion becomes way more stable. And in chemistry, stability is the name of the game. Okay, so we've got our alphabet, we've got the nuance of 3D shape. Now it's time to learn the grammar. These are the fundamental rules that dictate how molecules actually talk to each other. So much of organic chemistry boils down to one simple transaction: The exchange of a proton. The Bronsted-Lowry definition gives us the two key players. You've got an acid, which is a proton donor, and a base, a proton acceptor. That's it. This simple little handoff is behind a huge number of chemical reactions. So how do we measure how willing a molecule is to give away its proton? We use a special number called the pKa. Just think of it as a report card for acidity. And the rule couldn't be simpler. The lower the pKa number, the stronger the acid. Period.
Let's look at a real-world comparison. You take ethanol, its pKa is about 16. Then you look at acetic acid, its pKa is around 4.7. That is a massive difference. It tells us that acetic acid is a much, much stronger acid. And can you guess why? It's because when it loses its proton, it forms that acetate ion we just talked about, the one that's super stable because of resonance. See, it's all connected.
All right, this is where it all comes together. We've done the alphabet, the nuance, and the grammar. Now we can finally start building our vocabulary by learning to recognize the major families of molecules that populate the organic world.
When you put all these ideas together, the bonding, the 3D shape, the stability, the reactivity, what you get are these specific arrangements of atoms called functional groups. Think of these like common phrases or idioms. They're families of molecules, and each one has a really predictable chemical personality.
And here's just a tiny glimpse of this new vocabulary. You've got alcohols, which have an OH group. There are amines, which are basically cousins of ammonia. Then you have ethers, carboxylic acids, and alkenes, which have a reactive carbon-carbon double bond. The cool part is, once you can spot these groups, you can start to predict how even gigantic, complex molecules are going to behave. So, here's the bottom line. Organic chemistry is not about memorizing an endless list of facts. It's about understanding the language. Once you get the alphabet of atoms, the nuance of their shape, and the grammar of how they react, you suddenly have the power to read, write, and even predict the conversations happening in the molecular world. And that kind of leaves us with a final big picture thought. If molecules really do speak a language of sharing electrons, trading protons, and shifting their shapes, what kind of incredible conversations are they having right now, all around you and even inside you, creating the world we experience every single moment?